Okay, so welcome to this next video in the playlist on cis-loop ligand-gated ion channels. And in this video what we're going to do is discuss the 5-HT3 receptors. So we have seen how there are four main examples of cis-loop ligand-gated ion channels, which are the nicotinic acetylcholine receptor, the 5-HT3 receptors, okay, and then the GABA-A receptor and also the glycine receptor. So in this video what we're going to talk about is specifically the 5-HT3 receptor, which is an example of a cis-loop ligand-gated ion channel. Okay, so let's start by discussing the structure of the the 5-HT3 receptor. Okay, so let's say here that we have the phospholipid bilayer, and within the phospholipid bilayer we have our 5-HT3 receptor sitting here. Okay, so it's a cis-loop ligand-gated ion channel, which means that it has a pore which allows ions to move through it. And when the ligand arrives and binds to the receptor, that causes the pore to open. Okay, now all cis-loop ligand-gated ion channels have 5 subunits making them up. So 1, 2, 3, 4, 5, like that. So the channel basically is made up of 5 proteins stuck together. Okay, and this is true of all cis-loop ligand-gated ion channels. So 5-HT3 receptors are an example of a cis-loop ligand-gated ion channel, which is often abbreviated to LGIC for ligand-gated ion channel. Okay, right. Now, let's take one of these subunits that makes up this pentameric structure here out, and let's have a closer look at its structure. Okay, so let's look at its membrane-spanning topology. Right. So if we take one of these proteins out that makes up the pentamer here, which is the overall receptor, then what we find is that its membrane-spanning topology looks like so. Okay, so here we go. Basically, at the start, it has what's known as a cis loop. Okay, and I'll discuss what a cis loop is in a moment. Then, I'll start off with the amino terminus, that'll be good. So here's the amino terminus of the protein. Then it goes through this cis loop. Then it begins to span the membrane, so it spans the membrane once. It then spans the membrane a second time, and the third time, and the fourth time. And then here is its carboxyl terminus. Okay, so, as promised, I'm now going to discuss with you what a cis loop is, because it's after this that the cis loop ligand-gated ion channels are named. So, the cis loop ligand-gated ion channels is a whole family of ligand-gated ion channels, and they all basically have this same membrane-spanning topology here with a cis loop in their amino terminal extracellular domain. For this is the extracellular fluid side here, and this is the cytoplasmic side of the phospholipid bilayer. Okay, so now let's discuss that cis loop in a bit more detail. So basically, the reason it's called a cis loop is because it is held together by disulfide bonds forming between cysteine residues, which CYS is short for cysteine, on the 2 opposite strands here. So let's show these. So let's say here's one of these strands. So let's say the strand I'm talking about at the moment is this strand here in purple. So we're starting off with this purple strand, okay? And let's say it's got a cysteine in here. So here's the amino terminus of the cysteine, the alpha carbon, the R group coming off the cysteine amino acid, and it will have a thiol group there, but the thiol group is going to be involved in a disulfide bond, so I won't put the hydrogen on. Then we have the carboxylic acid group of this cysteine, and then it loops round, okay, onto this other opposing strand here. And then what you'll have is the amino group of this cysteine again, so you'll have another cysteine amino acid in this opposing portion of the polypeptide. Here's its amino group, here's its alpha carbon, the methylene group, and then it will have a thiol group as well. But this thiol group will now be bound to that other sulfur atom on the cysteine residue on the opposing polypeptide strand. This alpha carbon will also have a hydrogen, and then it will have its carboxylic acid group, and then it will continue on. So this is what is meant by cis loop. It's this loop in the polypeptide structure held together by this disulfide bond here. And disulfide bonds are also often referred to as disulfide bridges because they're bridging the two polypeptides. Well, the two polypeptide strands in this case, because it is actually the same polypeptide. Okay, right. So that's why these are named cis-loop ligand-gated ion channels, because the structure of the monomer, which makes up the pentameric receptor or ion channel over here, it has this cis-loop within it. And indeed, all cis-loop ligand-gated ion channels have this cis-loop structure here. So 5-HT3 receptors are an example of a cis-loop ligand-gated ion channels, but there are others which I listed off at the start. So the nicotinic acetylcholine receptor is another one, the GABA-A receptor, and the glycine receptors in the spinal cord are also examples. Okay, right, so you make 5 of these proteins and you put them together into a pentamer here, and you have then got your 5-HT3 receptor. Right, okay, so how many genes do we have coding for these subunits that make up this channel? Is there just one gene? That would be very nice, wouldn't it? If there was just one gene and then you just copied this gene 5 times and then you had your 5-HT3 receptor. Unfortunately not. There are 5 genes in the human genome that code for subunits of the 5-HT3 receptor. Okay, and these are cunningly labeled 5-HT3A, so the 3A gene, the 5-HT3B gene, and then it goes on, 5-HT3C, and I suppose I've only got 2 more to go now, so I'll continue on, 5-HT3D, and finally 5-HT3E. Okay, so we have these 5 genes through A through E, which all code for proteins that straddle the membrane like this, and they can all be used to make 5-HT3 receptors. Now, the question is, how do you assemble them? Do you take 5 of one and put them together to make a homopentamer, or can you mix and match basically between them? Well, what we have found, what we know so far, and I want to stress that the 5-HT3 receptor is nowhere near as studied as the nicotinic acetylcholine receptor, so much less is understood about these. What we know is that you can make homopentamers out of 5-HT3 receptors, 3A rather. You can make homopentamers out of the 5-HT3A subunit. So you can use this gene, you can produce 5 proteins from it, you can slot each one of these proteins into these 5 slots, and you'll then have a 5-HT3 receptor, which will be a homopentamer of the 5-HT3A subunit. Okay, and that's often referred to as the 5-HT3A homopentamer, or just the 5-HT3A receptor. Often people will put homopentamer so that you know exactly what we're talking about, but if people just refer to the 5-HT3A receptor, then generally they mean this. Or if they just say the homopentamer 5-HT3 receptor, then it's assumed that they mean this, because as I'm going to show you, there's actually very few 5-HT3 receptors that we've elucidated. Now, the other one that we know exists in humans and is important is a heteropentamer of 5-HT3A subunits and 5-HT3B subunits. Okay, so oops, we've run out of space. Heteropentamer. Okay, so when you build a heteropentamer of 5-HT3A and 5-HT3B, then what you're going to do is you're going to make some 5-HT3A proteins, and you're going to make some 5-HT3B proteins, and you're going to need 5 overall subunits, and you're going to stick them together. Now, I'm being very vague here. I would love to tell you exactly how many 5-HT3A subunits you make and exactly how many 5-HT3B receptors subunits you make. So for instance, I'd love to tell you that you make 3 of this one, 2 of this one, and then I'd love to tell you how you stick them together. That is not known, I don't think, at the moment. Okay, all we know is that you have 5-HT3 receptors where some of the subunits are 5-HT3A proteins and some of them are 5-HT3B proteins. We don't know the stoichiometry and we don't know the actual positions of them relative to one another. And this heteropentamer is often referred to as the 5-HT3AB heteropentamer. So it's got the AB there to denote that it's got A and B subunits in. Okay, so we have this homopentamer and this heteropentamer, and these really are the only the only 2 main 5-HT3 receptors that we understand at all. I think we also know that you can also make heteropentamers of 5-HT3A with 5-HT3C, and also with 5-HT3A and 5-HT3D, and also with 5-HT3A and 3E. So it seems as though it is utterly necessary to have the 5-HT3A in, and then you can mix it with these other 4 here to make heteropentamers. So either you can make a homopentamer of 5-HT3A, or you can mix in one of the other 4. And the stoichiometry of how you mix it is not known. And these other heteropentamers, where you're using the 5-HT3C, 5-HT3D, 5-HT3E subunits, very little to nothing is known about them, and they're not thought to be that important. Okay, so really, as far as anything reasonable is concerned, the only 2 5-HT3 receptors that we need to worry about are this homopentamer of 5-HT3A and this heteropentamer of 5-HT3A and 5-HT3B. So this is quite nice. Basically, all that is known is that we have 2 of these things. This one, the 5-HT3A-B heteropentamer, and this one, the 5-HT3A homopentamer. Okay, so that's quite nice and simple. Right, now, what I'm going to describe to you now is an experiment that can be used to show how similar how similar cis-loop ligand-gated ion channels are to one another. Okay, so what we're going to do is we're going to take these 5-HT3A proteins and we're going to experiment with how similar they are to the alpha-7 nicotinic acetylcholine receptor subunit. But we'll do that in the next video.